in our previous lecture we discussed about surface tension driven flows. Now the issue is that surface tension driven flow is a very important consideration for biomicrofluidic applications, but it is also critical to figure out how you can modulate surface tension, because you can add an additional controlling parameter over your surface tension driven flow if you have a surface tension driven flow in the basics and then a strategy by which you can modulate the surface tension. So we will today try to identify that what are the various ways by which we can modulate surface tension. So normally one can have a wide variety of microflow actuation mechanisms by introducing gradients in surface tension. So surface tension itself is a force, but you can also have a control over that force by creating gradients in surface tension or variations in surface tension. So you can generate gradients in surface tension force by generating gradients in temperature, gradients in concentration, you can create an electric field, you can modulate the contact angle by making a surface hydrophobic or hydrophilic. That means that maybe you can generate a gradient in surface tension by making a portion of the surface hydrophobic and another portion of the surface hydrophilic. So it is possible that you can use a combination of all these effects together to bring out very interesting facets of surface tension driven flow. So to summarize, the basic is surface tension driven flow, but you can also have gradients in surface tension by having gradients in certain field variables like temperature, concentration and so on. So with this little bit of background, we will start with how temperature gradient can be used to drive a flow by creating a surface tension gradient. So in the slide there are a couple of examples. I will go through these examples, but before that I will like to go through a very classical example which is used in manufacturing processes. So let us go to the board and try to explain this. So let us say that there are two pieces of materials which need to be joined, and how are you going to join these two pieces of materials? Let us say you strike an electric arc or a laser to create a local heating in this region, and in the process this material can get molten. So a melt pool, say covering this much region, not exactly rectangular melt pool will be created, but just to give you an idea, say locally over this region the material gets molten. Now if you see here, the temperature of the material is high, and normally for many materials the surface tension decreases with increase in temperature. So here the temperature is high, that means the surface tension is low. Further away from this in the molten region still the temperature is low, so the surface tension is high. Therefore there will be a force on the fluid in the molten region from the higher temperature to lower temperature, that means from lower surface tension to higher surface tension. So once this is created, this flow will eventually come down by gravity effect and will come up by buoyancy. So a nice circulation loop will be created to make sure that there is a continuity in the flow. Similar flow pattern will be there on the other side like this. So, with this fluid flow, now if you have and it is not that this fluid flow is confined only in this and this fluid flow is only confined within this. So, in this process these two materials can interact because this flow can penetrate here and this flow can penetrate here. So, in this process there can be mixing, and after this material freezes, this mixing will give rise to the final microstructure and the material properties. So, this is a very important process which is known as Marangoni convection, or a convection which is driven by a thermocapillary effect, that is surface tension variation with temperature. Now, coming back to the slides, we will try to show some effects where the thermocapillary effect can be used to drive droplets and bubbles in microfluidic channels. So, here let me point it out, you will see that there is a droplet and this is a temperature gradient. So, what you are paying for, see it appears that you are paying for nothing to make the droplet move, but actually you are paying a cost by creating a temperature gradient on the surface. So, if you create a temperature gradient on the surface, see this end of the droplet is at higher temperature, that means lower surface tension, and this end is at a higher at a lower temperature, so higher surface tension, that means the droplet will migrate in this direction. For gas phase the surface tension dependence with temperature is different, so bubble if it is there it will move in the other direction. Okay. So, we have seen that how to control surface tension by using temperature. Now, we will see how to control surface tension using certain chemical species called as surfactants. So, surfactants are the compounds, surfactant, the full form of surfactant is surface active agent. These are compounds that lower the surface tension or interfacial tension between two surfaces. This may be between two liquids or a liquid and a solid. So, these molecules are essentially attracted by interfaces, and small volumes of these surfactants can change the weighting behavior completely. So, by lowering the surface tension, these surfactant molecules act magically, and they have applications in many areas like emulsification, detergents like soaps will have lots of surfactants, micelles, and you can create a typical surfactant molecule with a hydrophobic head and a hydrophilic head and a hydrophobic tail, and that kind of configuration is very common in many of the applications where surfactants are used to control the surface tension. Now, let me come to a third example where you can control surface tension by hydrophilization. So, hydrophilization is like let me give you the perspective. See, most of the surfaces on which microfluidic experiments are intrinsically done are hydrophobic in nature, like PDMS, PMMA, they are mostly hydrophobic in nature. Now, if you want to make them hydrophilic, so what you do? You can do a couple of things. One is, it depends on what you actually want to do. Do you want the hydrophilic characteristic to be permanent, or do you want the hydrophilic characteristic to be temporary? If the hydrophilic characterization is supposed to be temporary, then this is what you can do. You can do oxygen plasma activation. So, here what you do is that you arrange for surface reactions with reactive molecules. So, basically this ensures that you have polar groups on the surface, and these polar groups will attract water molecules, and that will make sure that it is a hydrophilic surface. So, oxygen plasma treatment is a very common strategy, and in most of our labs we do that. The problem is that this is not a permanent solution. So, after a few hours this hydrophilization effect will go away. So, alternatively what you can do, that you can coat with a hydrophilic material like Pitox for example. This is long lasting, but it is costly. So, in your lab if you want to decide on what method you will be using for hydrophilization, you have two choices. One is a cheaper method, but it does not last for long, but for most of our experiment it is good enough. But if you want to have a long lasting method, you have to go for a more expensive method. Okay. The next effect is something on which I want to spend a little bit of time. This is regarding controlling surface tension by electrical effects. So, imagine that there is a microfluidic substrate, say glass, on which you have coated some electrode. So, typically ITO coated glass for example. So, in the figure which is shown in the slide, you have the electrode at the bottom, and on the top of that you want to have an insulator, and typically the insulator is designed with a purpose. So, the insulator itself can be some PDMS for example. So, the purpose of the insulator is to act as a capacitor and store some charge, and then you can have a part of the insulator as a very thin hydrophobic coating, which may be for example Teflon. So, the whole idea of having a hydrophobic coating is that on the top you have a nice droplet which is formed. So, if you have a droplet which is formed, the contact angle will be high, and then we will see that how by applying electric field we can lower the contact angle. So, if we lower the contact angle, a droplet which was sitting on the hydrophobic surface will spread on the surface, and because electric field makes the droplet spread on the surface, this phenomenon is called as electroweighting, or basically the surface is being weighted by the fluid due to electrical effects. Okay. So, if you look into the slide, this is the very important formula, and I will come to the derivation of this formula. This formula relates to what is the difference between the contact angle with electric field versus without electric field. Okay. So, if theta prime is the contact angle with electric field and theta is the contact angle without electric field, then the formula which relates the new contact angle with the old contact angle is given in the slide, and I will explain the symbols of the formula, and in a moment I will come to the derivation of this formula. So, cos theta prime is equal to cos theta plus half CV square, where C is the capacitance per unit area, and I will show you how the capacitance comes. Basically the capacitance comes in a very simple way. So, if you have a battery connected system between the electrode and the liquid, then you will see that there is a charge which eventually goes from the battery and gets stored in the insulator. So, the capacitance of this insulator, this insulator can now, this entire system can now be imagined as a parallel plate capacitor. So, if it is imagined as a parallel plate capacitor, the capacitance is given by epsilon by d, where d epsilon is the permittivity and d is the thickness of the insulator. So, that C is that capacitance per unit area, sigma LV is the liquid vapor surface tension coefficient and V is the voltage. So, from here you can clearly see that there is one very important finding from this formula. So, the formula says, if we look into the formula again, the cos theta, nu cos theta is a function of old cos theta plus a parameter which is proportional to square of the voltage. So, whatever may be the sign of the voltage, V square is always positive. So, if V square is positive, you will have cos theta prime is always greater than cos theta, because capacitance, sigma LV, all those are also positive. That means theta prime is less than theta. So, it is always electroweighting, no matter you apply positive bias, negative bias or whatever, it cannot be an increase in contact angle because of electric field, it is only a decrease in contact angle because of electric field. So, now I will just briefly tell you about two very interesting observations. So, one observation is, so let me write down the formula in the board so that we can explain these observations. So, just for simplicity I am writing this. Now, this gives you an appearance that if you increase this voltage, this will go down and it will go down and down and down like this, I mean forever, but it does not happen. It comes to a limit up to which if you increase the voltage, it does not come down anymore. So, the contact angle comes to a saturation stage. So, this phenomenon is known as contact angle saturation. So, if you look into this theta versus voltage, this VDC stands for a DC voltage. So, you will see that it will come to a saturation and with increase in voltage, and then it does not change anymore. So, this is one interesting phenomenon. The other phenomenon is that now if you reverse the bias, reverse the voltage, you will see that the way in which the contact angle got decreased is not the same way in which the contact angle got increased. So, there is a hysteresis. So, contact angle hysteresis and contact angle saturation are two very interesting phenomena, and believe me or not, no good theory, very good theory has yet been developed to explain this to the satisfaction of researchers. But if you look into the research of droplet based transport or droplet based microfluidics, you will see there is a lot of work on contact angle saturation and contact angle hysteresis. Okay. The next agenda will be to show you a very simple derivation of the formula, this cos theta prime versus cos theta, which is also known as Young-Lippmann equation. There could be many ways of deriving this formula, but I am trying to do this with the help of a simple school physics based approach. So, what is the approach? So, look into this figure. So, I am explaining this figure, and let me try to point the mouse, yes. So, here you have upon connecting the initially uncharged droplet to the power source, which is the battery here, there is a charge delta q that flows from the battery to the droplet and then to the electrode. So, what is the work done due to this flow of charge from the battery onto the system? So, the work done is the instantaneous potential times the delta q. So, V instantaneous into delta q, where V instantaneous is a function of the instantaneous charge given to the droplet. Now because you have that insulator, you have a capacitor system working, so your instantaneous voltage is Q by C, where C is the capacitance. So if you now substitute this, you will see that the total work done, where if you substitute V as Q by C, so Q dQ by C, so Q dQ is half Q square and Q square is C square V square, so it will become half CV square. So where VB is the potential of the battery. Now, so this is not the only component of the work. See, the battery supplies charge to the other part of the system. That means for the battery there is some flow of charge away from it. So what is the work done for the battery? The work done for the battery again is voltage into delta Q, but this delta Q is minus because charge has flown from the battery to the system. So for the battery it is minus delta Q, if it is plus delta Q for the system, it is minus delta Q for the battery. So it is VB into minus delta Q. See, the difference between the battery and the capacitor is that for the battery the potential is constant, for the capacitor the potential is building up from 0 to the maximum. So for the battery the work done is VB into minus delta Q with integral total charge, so that means that is minus CVB square. So that half parameter is not coming here because for the battery the potential is constant, whereas for the droplet the potential is varying from 0 to VB. So that integration is there. So what is the total work done? Total work done is half CV square minus CV square, so minus half CV square. So who will, where from the system gets energy to do this work? The system gets energy to do this work by utilizing the solid liquid interfacial energy. So that means you can say that the sigma SL okay. So because this is, all these are per unit area, this also you can express as per unit area, okay, because surface energy or this surface tension can be expressed as energy per unit area. So if this is the energy per unit area, this should also be capacitance per unit area, so that the units are balanced. So you may write it as small c maybe, okay. So electrowetting, what it is doing? Is it changing the liquid vapor surface tension? No, it is actually changing the solid liquid surface tension, because here it is very logical. Here your interface is solid liquid interface, that where the charge is coming into storage. It is not the liquid vapor interface, it is not the air droplet interface, it is the substrate droplet interface. So now if you have a droplet like this, this is liquid, this is vapor, this is solid, this is sigma LV, so this force balance we did earlier, but I am just repeating it in case you have forgotten. So sigma LV cos theta plus sigma SL is equal to sigma SV. This is the force balance along the horizontal direction. With the, after applying the electric field, the cos theta will become cos theta prime, sigma SL become sigma SL prime, sigma SV remains the same, okay. So now you subtract one from the other, so sigma LV into cos theta prime minus cos theta plus sigma SL prime minus sigma SL equal to 0. You just subtract these two equations. So, sigma SL prime minus sigma SL is minus half CV square So, you have cos theta prime is equal to cos theta plus half CV square by sigma LV, which is the Young-Lippmann equation. Okay. So, this formula is elusive because by looking into this formula you will get a feel that as if it is the sigma LV that is creating the change. It is not sigma LV but sigma SL or LS that is creating the change. Okay. So far so good, but how can you use this in biomicrofluidics? Remember, this is a course on biomicrofluidics. So we need to draw an interesting context in which it can be brought to the applications of biomicrofluidics. So now how can we use this principle to make a droplet move? So let me now say that you have a surface on which you have a droplet. Now if you apply electric field, what will happen? Say uniformly this droplet's contact angle will go down, so it will become like this, but this is not moving, this is just spreading. So if you want the droplet to physically move from one place to the other, what you can do? You can create a differential in voltage across the two ends of the droplet. So technically you can put this with voltage biases V1 and V2, where V1 is different from V2. So with V1 different from V2, depending on whichever is more and whichever is less, it may be possible that there is a difference in contact angle on the two sides. So maybe an asymmetry is created. Because of this, wherever the contact angle is less, the surface tension force is more, and therefore the droplet will be drawn towards that direction. So if you have a contact angle theta 1, if you have a contact angle theta 2, depending on the difference between theta 1 and theta 2, there will be a net force which will make the droplet move. So technically you can make an array of electrodes, and this is a design of algorithm and computer science, that you fix up what will be the time duration and what will be the sequence in which these electrodes will be switched on and off like that, so that the droplet moves from one point to another in an optimal path at a shortest time. So this is how one can design algorithms for making a droplet move on a microfluidic system, and each droplet, if it carries one bit of information, then this entire paradigm of conveying information from one source to another destination is known as droplet based digital microfluidics. So how this droplet can be moved from one place to another? To explain you that, I will go through a couple of movies which are based on experiments done in our own lab. So here you can see that there is a droplet, and these black things what you see here are electrodes. So these electrodes are switched on and off, and you see how this droplet is hopping from one electrode to the other. So now let us say that, come to this picture here, let us imagine that this red colored drop is a blood drop and this white colored drop is a reagent. Now we want that this reagent will go from its source to the destination where the blood sample is kept. It will react with the blood and show a change in color, and by this change in color a disease can be detected. So let me show you how this is done. So this droplet is moving, see it is moving, and then it fuses with the blood droplet, and once it fuses with the blood droplet there may be a change in color. So by grabbing the colorimetric signal, one can give a fruitful indication of a diseased condition that is prevalent with the blood sample. So we started with some basics of how electric field can modulate surface tension, and then we could come up with some interesting applications in biomicrofluidics where such fundamental science can be used. Thank you very much for your attention to this important topic on modulation of surface tension. We will consider a new topic in the next lecture. Thank you very much.